let's talk a little bit about exergy. So think about a fire. You have fuel and oxygen and you get waste products and heat off of it. But after that, what do you have, right? You just have waste products. So it had the potential to accomplish something, but it wasn't really used. Maybe you warmed yourself with it, maybe you cooked some food, but the rest of that energy and now this waste product is just going to go to waste. So we'd like to have, as engineers, a way to quantify potential for usefulness. So exergy is that quantification. Exergy is somewhat like entropy. It's one of those things that's not conserved, and the reason it's not conserved is irreversibilities, primarily friction and heat loss through a temperature difference. So conceptually, what is this? It's the maximum theoretical work that a body could do before coming to equilibrium with its surroundings. So we need to come up with a definition of what this reference surroundings will be. It's going to be the environment. It means it's large enough to absorb any heat transfer without making really any measurable difference to the surroundings. There's a lot of air around my house right now as I'm sitting making this video. Whatever I do is not really going to change the outside significantly. Now, typically we assume that the surroundings are 25 degrees C and 1 atmosphere, but that's somewhat arbitrary. It's really dependent a little bit on where you are and what your circumstances are. So the dead state is going to be this reference temperature and pressure. If something is at the dead state, it has no potential for doing work. So exergy is the maximum theoretical work obtainable from an overall system that consists of a system and the environment as the system comes into equilibrium with the environment, or we could say as it passes to the dead state. So let's look at formulas that would quantify the exergy of a system. So it's really changes in various forms of energy. So I'm going to, if I think of a closed system, I have a bottle of stuff with energy, okay? It's at a temperature pressure. That means it has an internal energy and so forth. Maybe it's moving. So the U of my material minus the U it would have if it were at the dead state, plus the pressure of the dead state or the surroundings, times the volume difference between these two, minus T naught times delta S. So this is like a work, and this is like a reversible heat transfer, all at the temperature of the dead state. And this would be all at the pressure of the dead state, plus any kinetic energy or potential energy. Now, I don't have a difference here because the dead state does not have a velocity or a height potential energy quantity there. Now, I can do this as either an extensive or an intensive. Okay, the notation is interesting because in this textbook, at least, they use a bold capital E or lowercase e for exergy. The non-bolded E's that you see spattered throughout the book, such as in KE and PE here, are for energy. So when I see just an E that's not bold, I mean total energy, internal energy plus kinetic energy plus potential energy. And if I see it bold, that's exergy. I think that's fairly subtle, so if you're not sure, be sure to either ask somebody what is meant or look for those subtle verbal clues so that you can figure it out. Now, the dead state is going to typically be the same from one problem to the next, and so you can go ahead and get that information for the tables that you have in your book and save yourself some time later as you're working problems. So if we look at steam, I have a 2.5 kilogram sample of steam. It's at 500 degrees C and 1 megapascal, and I'm holding it at a height 1.4 meters above the ground. What's the exergy of this 2.5 kilograms of steam? Well, so I need data for the steam and for steam at the dead state. So at 500 degrees C and 1 megapascal, I find this information. At 25 degrees C and 101 kilopascals, I find this information. Okay. So now let's go through and do the calculations. I broke this up into different terms. So my internal energy is the mass times the difference in those U values. P delta V is the pressure of the dead state, not the actual pressure, but the dead state pressure times the volume difference, times the mass because I want total volume. The reversible heat transfer at the dead state temperature is T delta S, so 298 Kelvin. And again, subtract off those S's, multiply by the mass. I have no kinetic energy because they didn't mention a velocity, but potential energy, I do have that, and it's 1.4 meters above ground level, so take my 2.5 kilograms, G is 9.81 meters per second squared, an altitude of 1.4 meters, and then adjust the unit so I can get kilojoules like everything else here, so I'll divide through by 1,000. Now this is very small compared to the others. There's not going to be a lot of energy gained by dropping steam 1.4 meters. Steam is a gas, and so moving a gas such a small height is really going to be a very minimal contribution. But I appropriately add or subtract these, and I come up with a value of 2,129 kilojoules. Now, the interesting thing is that is positive, and the answer will always be positive, no matter whether I have something hotter at higher pressure or colder or at lower pressure. The answer will always be positive. So to see that, let's look at an ice cube at 0 degrees C. Again, the data for at the 0 degrees C solid and at the dead state, which would be a liquid at 25 degrees C. And when I do that calculation, I get a positive answer. So the answer for exergy will always be positive. So there's some little facts that are both interesting and helpful in understanding why anyone cares about this. So it's a measure of how the state departs from the environment. Okay? It's a way for me figuring out that, oh, this is a stream that has a lot of potential to it, or this is a stream that has very little potential. Now then, when I calculate the exergy, my answer will always be positive. Okay, you cannot get negative. It will be 0 if I am at the dead state. Exergy is never conserved, but it's destroyed by irreversibilities. The only way I can get exergy of 0 or exergy changes of 0 will be if I assume reversible processes with no heat transfer. Now, we've talked about exergy as the maximum theoretical work, but it also could be the minimum theoretical work required to bring the system from the dead state to the given state. So you can look at this either way. It's just a matter of point of view. And then the last of these little facts, and where I want to close this video, is that a system at the dead state is at thermal equilibrium, meaning the temperature can't change, and it's at mechanical equilibrium with the environment. So mechanical equilibrium is when I have the pressure no longer can change. So I have no forces at work. This is the definition of thermodynamic equilibrium. So at this point we will close. We'll come back and have a second video over some of the basic facts of exergy.